Welcome to today's AM Academy webinar, part of our ongoing series that's designed to make cutting-edge materials science and engineering knowledge more accessible. My name is Zara and I'll be your host for this session. And today's talk is on combining annular microreactors with machine learning, optimizing Vaterite yield and productivity. I'm very pleased to introduce Dr. Maxim Kiryukhin, who is a technical project manager at Accelerated Materials. And in this session, Maxim will dive deeper into the key properties of Nano Vaterite and its emerging industrial application, production challenges at scale and how to overcome them, the synthetic pathway using our K1 annular reactor, and how AM Learn enables smarter optimization for yield and productivity. We'll also leave some time at the end for a Q&A, so feel free to drop your questions into the Q&A box throughout the session. And with that, I'll hand over to Maxim to begin. Over to you, Maxim.
Thank you, Zara, for your kind introduction. And it is my pleasure to have you today with me. I would like to share about my very recent data, an outcome of a short research project, which I led in Kazakhstan, in the Eurasian National University in Astana, where I have read as a guest professor a course on nanochemistry and nanotechnology, and also led practical works on nanotechnology with the third-year students of the Department of Chemistry. And let me just share my screen. See my presentation.
Yeah,
perfect. Right. So this was actually the story of calcium carbonate, nanoparticles of calcium carbonate. There are three allotropes of calcium carbonate. The one and probably most common is calcite, like for example, chalk is made of calcite. The other one is aragonite, which is usually formed at a high temperature and pressure, and the sea organisms, deep sea organisms, they made their shells out of the aragonite. And the third one, Vaterite, was named after the German geologist of 19th century, Henrik August Vater. And this is the least stable form of calcium carbonate. Still, it can be found in nature in some very special places, like for example, in the Canadian high Arctic, in the waters rich with calcium sulfate, gypsum, and where it is extremely cold and the humidity is very, very low. This is where Vaterite is actually formed. And also some plants and animals also are producing Vaterite, like for example, this plant growing in the mountains area of Alps. It has calcium carbonate crystals on at the ornament of the leaves, and these crystals are made of pure Vaterite. This kind of need-like structures are made of Vaterite. They're covering these squirts living in the deep seas. But what is so special with the Vaterite? What defines its applications? In the first place, Vaterite is very porous structure, which gives opportunity to use it as water filters, as air purifiers, or to load those particles with some molecules of interest for drug delivery, as anti-corrosion coatings, as sensors. And also, as I said, this is very unstable structure. The Vaterite tends to recrystallize into its more stable form, into calcite. And during this process, you may initiate a burst release of whatever molecules loaded in their particles. So these two properties, the high porosity and tendency to recrystallization, it defines their applications. If we look at the loading capacity of vaterite towards molecules of interest, it really depends on the molecular weight of the cargo molecules. Like, for example, for relatively small molecular weight enzyme, it may be up to 5 weight% in the vaterite. With the increase of the molecular weight of the protein, its loading capacity decreases to about 1 weight%. Although there are some exceptions, and some particular proteins, like, for example, alkaline phosphatase, there was reported extremely high loading capacity for this particular substance, up to 16 to 20 weight%, which is probably determined by the surface chemistry of this protein. And there are also different ways to improve the loading capacity. The most common are a co-precipitation approach, where the vaterite are formed in a solution of the molecules of interest, and they go into the structures once they are forming. This allows to increase the loading capacity slightly. For example, for BSA, it goes up to 28%. If you use consecutive adsorption cycles, then you also can increase the loading capacity, in this case up to 4 weight% after 7 cycles of absorption. And there are some special techniques like freezing induced loading, for example, when the ice growing crystals, they push proteins into the vaterite structures. And in this case, you can achieve incredibly high 13 weight% of a BSA in the vaterite particles. But you need to be careful a bit here. Like, for example, in this particular case of lactoferrin, which is a whey protein and major component of human breast milk. And it has numerous health benefits, but unfortunately, when it is just consumed by adults, it is fully digested in our stomach, losing all the health benefits. And in order to protect it from gastric digestion, people are using various types of encapsulation techniques. Vaterite is one of those applications. But when you are doing, for example, trying to load vaterite with lactoferrin by co-precipitation approach, because of very high alkaline, very alkaline pH of the solutions, lactoferrin is destroyed, and actual loading capacity becomes quite low. And you need to be very careful here. So when you use some buffers during the synthesis, then really you can increase the weight percentage of lactoferrin inside the particles. In a post-loading approach, as I mentioned, the loading capacity is lower, and it increases linearly. The amount of lactoferrin increases linearly with the increase of the amount, for example, of vaterite particles introduced to a solution of lactoferrin, while keeping the weight percentage of lactoferrin nearly constant, which is an indication that the particles are fully saturated with the protein. Another factor which also affects the loading capacity is the size and morphology of the vaterite particles. Like, for example, here you can see that when we go from larger spheres to a smaller spheres, the surface area increases dramatically, and open porosity also increases, and you can expect much higher, up to 2 times higher loading capacity of in this case it was dextran labeled with fluorescent dye rhodamine, and when you go to ellipse particles, which have a higher surface area compared to sphere, you also can increase the loading capacity of those molecules. As I mentioned, vaterite is not very stable, and it tends to recrystallize. And this process, it also depends on the composition of your solution. For example, a pure calcium carbonate, it quite rapidly recrystallizes into the into the calcite. And if the smaller the particles, the faster this process is going. However, when you have some molecules of interest, like alkaline phosphatase in this particular case, absorbed into the structures, then the process of recrystallization it is very much delayed, and you can extend the existence of vaterite particles all the way to 20 hours after continuous stirring, right? The process of recrystallization, it dramatically increases in the presence of salts, and here the survival of calcium carbonate is much shorter compared to salt-free solutions. But in the presence of, again, when the particles are filled with molecules of interest, this process, even in a salt solution, can be quite prolonged. So all depends on the conditions, actually. If you're doing the same in a phosphide buffer solution, then you can immediately convert your calcium carbonate into hydroxyapatite, which is quite understandable in the presence of phosphide ions. And what does it mean, this recrystallization, for the process of the release of our molecules of our drugs out of calcium carbonate, right? In contrast to, for example, porous silica particles, when the release has this usual kinetics reaching saturation within a few tenths of minutes. In case of calcium carbonate, it is a bit different, right? And you can see that like in water solutions, the burst release is happening when the particles start to recrystallize from the vaterite, very porous vaterite form, into the calcite form. Like, for example, for low molecular dyes like rhodamine, this happens after about 4 days of mixing. You can have this very burst release. In case of larger particles like more molecules like dextran, this happens even after longer time of 6 days. And again, you can have this kind of burst release, in contrast to, for example, ethanol solutions where no recrystallization can happen, right? And you don't have any kind of this release systems. Interestingly, calcium carbonate particles, these vaterite particles, then can easily penetrate into the cells, probably by endocytosis or some other mechanisms. And up to 70 particles can be incorporated by a cell. And with time, nearly all cells have the particles inside them, right? And by this approach, you can deliver drugs to cancer cells, because they can take their membranes is usually more permeable, and they can take vaterite particles much easier compared to normal cells. Like here in this example, you can see a mice which left leg it had a tumor, while the right leg was normal. And you can see that when you just inject the anti-tumor drug into the mice, it distributes evenly across all the organs, right? But when you inject these vaterite particles with the drug, it tends to accumulate in the tumor, while in the normal cells, its concentration is much less. And then in this particular case, it was kind of a photosensitizer drug, which activates upon irradiation with laser. And that is where once you start irradiating, the cells are just killed. And you can see that in case of this calcium carbonate particles containing the drug, all the cells were killed after this kind of laser irradiation. Also, vaterite particles, they are widely used for making gels. In this particular case, it was gel and gum gels, where calcium ions are known to induce the formation of the gel by complexing with the carboxylate groups of the gel and gum starch molecules. And calcium carbonate, these vaterite particles can be a source of these calcium ions, and their incorporation into the solution of gel and gum induces gelation. This process can be further facilitated if you have a mixture of calcium carbonate and magnesium carbonate, for example, because magnesium carbonate usually has much smaller size compared to calcium carbonate, and they are easier, they're dissolving easier, and you have this kind of a network of a gel where magnesium ions make a cross links, while the calcium carbonate particles containing your drugs can be trapped inside. This kind of gels, they were shown to have to be very good scaffolds for the cell growth. Cell like to grow in this kind of gels, and they stay there alive for quite a number of days without any trouble. So, like as you see, Vaterite particles, they have quite a number of applications. The only problem is that the methods of the synthesis are quite limited. Synthesis itself is quite simple. You are just mixing solutions of calcium chloride and sodium carbonate in a beaker, and if the temperature is higher than 60 degrees, then aragonite particles start forming. At room temperature, the vaterite particles or calcite particles can be formed. The challenge is how to prioritize the formation of vaterite particles and how to do this synthesis in the scale. Because there are like many factors which usually define the size and morphology of the calcium carbonate particles formed upon reaction between calcium chloride and sodium carbonate. Right. For example, when this reaction is performed in a mixed solution of water and ethylene glycol, the higher is the concentration of ethylene glycol, the smaller is the size of the particles formed, and you can go all the way from micrometer particles to sub-micrometer particles with the size about 500 nanometers, 300 nanometers even. Here also, by varying the ratio of calcium chloride to sodium carbonate and the amount of ethylene glycol in a mixed solvent, you can control the morphology of particles and convert them from spheres to like ellipsoid particles to kind of star-like particles and or cubical particles. The factors that define the process are usually time of the reaction, concentration of salts, viscosity of a solution, ratio of calcium chloride to sodium carbonate, pH, and also the volume of the reactor, and the effectiveness of mixing as well, which you can achieve there. All right, like here you can see that at a low temperature, like about 10 degrees, spherical particles tend to form. When the temperature becomes higher and higher, more and more like these star-like particles start forming. And at some point of the mixing, a recrystallization of the spherical particles into calcite and to formation of this kind of cubical particles start to happen. Both with spherical particles and with tunnel particles. At some point of time, the percentage of the cubical calcite particles become very high. In general, there are methods developed that allow us fabrication of spherical particles as small as 100 nanometer all the way to like 12 microns, elliptical particles with the size ranging from 800 nanometers to 3 microns, and star-like particles up to 3 microns in height, in size. A few reactors were specifically developed for this kind of synthesis. They are batch reactors that can control precisely the temperature of the synthesis, and you can follow the concentration of calcium ions, for example, with the calcium selective probes, and varying the time of the synthesis, temperature, and all these process conditions, you can control the particles morphology very precisely. But the problem is that all this works at a relatively small reactors, right? And the typical batch size is about 60 to 600 milligrams at most. All the attempts to like increase, to scale up this process, they actually failed because the mixing conditions in this case, they changed dramatically, and you cannot reproduce at a larger scale what you have achieved and optimize at a smaller scale. And it is a very big problem. And also like this tendency for the particles to recrystallize, they do not give you enough time actually to operate with at a larger scale. So this is where we try to come in, and we try to perform this synthesis with the help of our K1 reactor. So our objectives were first to maximize the content of vaterite and minimize the formation of calcite in the synthesis, and second, to maximize the process production rate. This is just a brief schematic of our K1 reactor. For those who hear this first time, it can be quite useful. So the reactors have this design, tube and tube and tube. In the first central tube, we supply pressurized air or other gas. And in the other two tubes, we pump in the liquids. So in this particular case, a solution of calcium chloride and a solution of sodium carbonate. So at the point where the first tube ends, the air meets with the first liquid, and it just presses the liquid towards the wall of the tube. And the thickness of this liquid film along the wall of the tube wall it depends on the flow rate of a liquid and of a pressure of air here. And we can control it. It may change from 20 to 100 micrometers. And then when the second tube ends, right, the air, it just presses first liquid into the second one. And this is where the mixing of the two liquids are happening. And again, the time of this characteristic time of this micro mixing, we can control it again precisely. It may be in the range of a few milliseconds, even below 1 millisecond, with liquid flow rates up to 20 ml per minute. And again, there could be different scenarios depending on experimental conditions. But in one most common case, we have essentially a laminar flow of liquid along the capillary tube and a turbulent flow of air in the center. And this turbulent flow, it generates kind of waves on the surface of a liquid. And these waves are what facilitate the mixing between the two liquids. And this is what how we can achieve very controllable mixing of the liquids, and in this way control the size and morphology of the particles formed upon the contact of these two liquids. So in this small animation, you can see this process again, how it is happening. So this is our reactor, tube and tube and tube, and two liquids are pumping through and mixing here. And this is upon this mixing, nanoparticles are formed. Yeah. So our reactor, it provides, as I said, very precise control over the mixing conditions and very reproducible mixing conditions as well. But the problem is how to find these optimal conditions in order to perform synthesis of your nanomaterial of choice, calcium carbonate vaterite particles in this particular example. And to do this, to facilitate the optimization of the process, we use machine learning algorithms. We have software, MLOn software, which provides this opportunity. So essentially, we're using this Bayesian optimization cycle, where the machine first generate initial set of experimental conditions. Then we perform these suggested experiments, provide to the machine algorithm the outcome of those experiments, and then machine tries to build a model using this data provided, right? And then find the best experimental conditions to achieve your project objectives. And it gives us the process conditions so that we run experiments again, measure results, add these results to the current database. And with these cycles and a few iterations, usually we can achieve material within the specs which we are going to get. So in this particular example of the synthesis of vaterite, we used four different process variables, which were the liquid flow rate, the flow rate of nitrogen. Here we use nitrogen as a gas supply, concentration of sodium carbonate, and ratio of concentrations of carbonate to calcium. So the AMLON, it generated the following conditions for the 6 experiments for us to run. And we performed this synthesis using a small batch size with a volume of about 50 milliliters per sample. And then we purified our product by centrifugation and washing with water. After 2 cycles, all the byproducts like sodium chloride are washed away, and we have a pure calcium carbonate. Then we performed drying of this product with a freeze dryer and characterize it with XRD, FTIR, DLS, and weight analysis to get data on process yield and production rate. So here you can see the XRD patterns of all the samples produced, and there are characteristic peaks of the vaterite labeled black here, and of a calcite labeled red. And you can see that in some samples calcite content was quite high, while on the others you nearly cannot see calcite peaks at all, right? And when we calculated like the amount of both vaterite and calcite produced in this case, we get this kind of data that content of calcite varies from 2 to 16%, depending on the conditions. And then we also calculated the productivity of each reaction. The data you can see here. The productivity depends largely on the concentration of chemicals used and on the flow rates, liquid flow rates. And then we provided this data to the AMLON software, and it tried to identify the best model, which appeared to be Gaussian model, which is actually quite evident because in our case, all the variables were like continuous. And the Gaussian model usually works quite well with this kind of variables. And then AMLON suggests us to run experiment at these conditions. So it provided us for the optimized liquid flow rate, nitrogen flow rate, concentrations of sodium carbonate, and the ratio of carbonate to calcium. And using these process conditions, we try to run the reaction using already much 10 times larger volumes, half a liter per each. And we produced a powder. Here you can see FTR spectrum and XRD pattern of the product, which is quite quality vaterite. In FTIR, we couldn't detect any signals of calcite at all. All peaks belong to vaterite. In XRD, we could see a bit of the strongest calcite peak here at about 29 degrees. And the calcium content was calculated to be about 3%. Here you can see the SAM images of those particles. They are mostly spherical. And the particles, they consist of, so these particles are a micrometer range scale. These are the dimensions which we get from DLS with D50 around 5 micrometers. But all of them, they consist of much smaller nanoparticles of about 50 nanometers. So this is how this process works. So we generate the calcium carbonate nanoparticles, which later tend to agglomerate and form this kind of larger micrometer size particles. And this is why those particles has so high porosity actually. And so just concluding, essentially in this student project, in 2 weeks, we managed to produce high quality vaterite at a production rate of about 300 milligrams per minute which was 100 times larger than a batch reactor commonly used. And essentially, we are currently studying the properties of this vaterite. We need to confirm that its properties in terms of drug loading and controlled release of drugs do not are not different from what you can achieve with batch synthesized vaterite. And this is end of my story. And I want to say thank you for the Professor Kopyshev, the head of Department of Chemistry of the Eurasian National University in Kazakhstan, Dr. Parakhonsky from the Ghent University in Belgium, who was actually a big expert in vaterite particles. He was working in this area for like up to 20 years, I think, already. And the beautiful students, group of third-year students from the Department of Chemistry who did most of this work, both synthesis and characterization. And of course, thank you for your attention, and you're very, very much welcome to ask questions if you have any.
Thank you so much, Maxim, for that great session. It seems as if we haven't had any questions come in, so thank you to everyone in the audience for joining us today, and we hope you learned a lot about combining annular microreactors and machine learning to optimize vaterite production.
Zara, I think we have some question here, right, in the chat.
Oh, yes, one's just popped in. We've had a question. Why is vaterite so unstable?
Yeah, so this is actually the property of this particular allotrope, that when you have in the presence of water, be it a suspension or even if this powder is stored in atmosphere with in the humid atmosphere, like what we have in Singapore, for example, it tends to recrystallize into calcium carbonate, into calcite, which is much more stable in these conditions. Vaterite is perfectly stable when there is no humidity. If you keep it, for example, under inert atmosphere, or if you keep it at lower temperatures, like in a freezer, then it is stable. But any humidity in the air, and it is recrystallizing. Does that answer your question?
Yeah, I think that's fine. We can give a couple of minutes if anybody has any other questions. Oh, another one's just come through. Why has vaterite then been preserved with the reactor?
Yeah, so the process of recrystallization takes time. It is not like happening immediately, and like in our case, so within hours, usually it is more or less stable. The process, if you take it for more than like 5 hours, then the content of calcite would be quite high. If you do your purification immediately after synthesis, and then start the drying, then you can expect to have very low calcite content. In our case, it was like still there was some calcite particles formed, 2 to 3%, but usually it is an indication of very high quality vaterite. If you have anything above 10%, then already not so good.
Perfect, thank you. See if there are no more questions, then I can wrap up a little bit early. So to everyone, a quick reminder that this webinar is part of our ongoing AM Academy series. So we share knowledge and tools to help accelerate materials innovation. And you can explore more webinars, articles, and technical resources at acceleratedmaterials.co/AM Academy. And we will be sharing the recording on our YouTube channel shortly. So if you do want to revisit any parts or share it with your colleagues, then please do keep an eye out. And thank you again, everyone, for spending your time with us. We really appreciate it. Have a great day, and we hope to see you at the next AM Academy session.
Thank you all. Goodbye.